Watch a complete overview of the thermal power generation process. This is a thermal power plant. During power generation, workers transport coal brought by train via coal conveyor belts to the power plant's coal feeder. The coal flows from the feeder into the pulverizer at the bottom. The pulverizer grinds the incoming coal into a fine powder. These finely ground coal particles then travel through air ducts to the coal burner. Here, the coal powder is ignited and the high-temperature heat generated is used to boil water. The initial water enters through these pipes. The water rises along the pipes and then reaches the boiler's economizer. The economizer improves the boiler's thermal efficiency and saves fuel. Next, the boiler water enters this steam drum. The steam drum separates water from steam. The water from the steam drum then flows to the dense network of pipes around the boiler, known as water walls. The boiler water descends along the water walls. As it flows, the boiler water absorbs heat generated by the burning coal powder, producing high-temperature, high-pressure steam. This steam then returns to the steam drum via pipes. The pipes at the top of the steam drum are steam pipes, and steam is represented in red. This separated high-temperature, high-pressure steam is then sent into the superheater for further heating. Here, the steam gradually transforms from a saturated state to a superheated state. However, the steam's temperature is still not high enough, so it is then sent into a second superheater to continue heating. There are several external pipes connected to the superheater. Once the specified temperature is reached, the superheated steam travels along the external pipes to the main stop valve here. The stop valve regulates the steam flow to the turbine, and in emergencies, it can completely block a passage of steam. Next, the steam reaches the secondary valves. These valves are controlled by the power plant's automation system, enabling them to respond quickly to changes in pressure and temperature to ensure the safe operation of equipment. Then, the steam passing through the valves travels through steam pipes to the turbine unit. There are three types of turbine units: high-pressure turbines, intermediate-pressure turbines, and low-pressure turbines. High-temperature, high-pressure steam first enters the high-pressure turbine through the pipes on its top. At this point, the steam pressure reaches 170 bar and the temperature reaches 540 degrees Celsius. Upon entering the turbine, the steam rapidly expands, causing the turbine to rotate at high speed. The speed can reach 3,000 revolutions per minute. Let's take a detailed look at how a steam turbine works. This is a small pinwheel. When we use steam from boiling water to blow on it, the pinwheel spins quickly. If we replace the pinwheel with a turbine blade, the blade will also spin. But there's a problem. A single set of blades leads to significant steam loss. To solve this, we can add another stator blade and a rotor blade. The stator blades do not rotate. They are only used to change the direction of the steam. When a large amount of steam enters from the side, it strikes the stator blades. After the steam changes direction, it hits the rotor blades, generating an upward thrust that drives the subsequent rotor blades to rotate. To ensure full utilization of the steam, we can add more rotor and stator blades, thereby generating more kinetic energy. If you observe closely, you'll notice that turbine blades resemble airplane wings. The top is slightly longer than the bottom, so steam travels a greater distance along the top. To cover more distance in the same amount of time, the steam velocity at the top must be faster. Faster flow means lower pressure. This results in higher pressure below than above, creating an upward lift that drives the blades to rotate. This is essentially the underlying principle of a steam turbine. However, there's a problem. After impacting the blades, the steam loses energy, causing its pressure to drop to just 85 bar and its temperature to fall to 340 degrees Celsius. Therefore, to further improve steam efficiency, the spent steam then flows out through the steam pipes at the bottom of the high-pressure turbine. This steam is sent into the reheater inside the boiler for reheating. Like superheaters, there are multiple reheaters. They are located at the top of the boiler. After being heated by the primary reheater, the steam then goes to the secondary reheater for further heating. Once heated to the specified temperature and pressure, the steam flows out of the boiler through this yellow pipe. Then, following the pipe, the steam first reaches the turbine's reheat valve. Like the main stop valve, the reheat valve also controls the steam flow into the turbine. It has a valve inside. When generator demand is low, the valve partially closes to limit steam flow and pressure. When power generation demand is high, the valve fully opens to maximize steam flow. After precise control, the steam then enters the next turbine, which is the intermediate pressure turbine. Like the high-pressure turbine, the intermediate pressure turbine rotates at high speed, driven by the high-temperature, high-pressure steam. Afterward, the spent steam then goes to the low-pressure turbine. Although the steam entering the low-pressure turbine has lost most of its pressure and energy, it is still sufficient to drive the low-pressure turbine. After passing through the high-pressure, intermediate pressure, and low-pressure turbines, the steam converts thermal energy into mechanical energy, driving the generator behind it to produce electricity. Next, let's take a detailed look at how a generator produces electricity. First, let's look at an experiment. This is a coil connected by wires to an ammeter. When a bar magnet is moved back and forth within the coil, the ammeter's needle also moves back and forth. This is because the coil cuts through the magnetic field lines of the magnet, generating an induced current. This phenomenon is called electromagnetic induction. The underlying principle of a generator is electromagnetic induction. A generator mainly consists of two parts, a stator and a rotor. However, unlike what was mentioned earlier, the generator's rotor does not use a permanent magnet. Imagine how complex it would be to accurately install such a large permanent magnet into the rotor slots. Even if it could be installed, the permanent magnet's magnetism would gradually decrease over time. So, how are these problems solved? Let's look at another experiment. This is a coil. When current passes through its ends, a magnetic field is generated around it. This coil acts like an electromagnet. This type of electromagnet is not very different from a common bar magnet. The only difference is that the magnetic field disappears when the electromagnet is de-energized. If the voltage is increased, the magnetic field continuously strengthens. Generators actually use electromagnets. It consists of 4 sets of coils. Since the electromagnets are initially unenergized, installation is very convenient. You just need to wrap the 4 sets of coils around the 4 protruding magnetic poles. This coil combination is also known as the excitation winding. For the winding to generate a magnetic field, it needs to be energized. Therefore, there is also a DC power supply here, connected by 2 wires to the 2 slip rings on the rotor. This way, the winding can produce a very stable electromagnetic field. For easier explanation, let's now take out one set of stator coils separately. When the rotor's magnetic field lines cut across the stator winding, according to the law of electromagnetic induction, an induced electromotive force is generated in the stator winding. When the rotor's end pole is in this position, only a few magnetic field lines are seen cutting the stator winding. However, as the rotor rotates, more and more magnetic field lines cut the stator winding, and the waveform generated is as shown. As the rotor continues to rotate, the magnetic field lines cutting the stator winding decreases again, and the generated waveform also begins to decline. After 1/4 turn, the S pole reaches this position, but the direction of the magnetic field lines is opposite to before. So, as the rotor continues to rotate, a waveform with the opposite direction is formed. This is what we commonly refer to as alternating current. Now we will add the other 2 sets of stator windings back, and the 3 stator windings are separated by a phase angle of 120 degrees. In this way, when the rotor rotates, we obtain 3-phase alternating current. The stator windings of synchronous generators use a star connection. The starting ends of 3 windings are connected to the live wires of the 3-phase AC. The ending ends of the other 3 windings are connected to each other to form a neutral line, which is connected to the neutral wire. Then, these components are placed into the stator frame, and a generator is assembled. When the turbine drives the generator's rotor to spin at high speed, the generator can then produce electricity. However, this type of generator has a problem. There's a large gap between the 2 magnetic poles, known as the air gap. If the rotor rotates at high speed, the air gap increases the generator's reluctance, reducing power generation efficiency. Therefore, thermal power generation typically uses this type of generator, which works on the same principle as the generator mentioned earlier. However, its rotor is cylindrical, without protruding magnetic poles, and is longer. And there is no air gap, so the rotor can spin at even higher speeds. Additionally, a longer rotor also generates a stronger magnetic field, which is why the generator produces more electrical energy. This electrical energy is then transmitted to transformers for voltage step-up, after which it can be distributed across the country. Now that we understand the principle of power generation, let's return to the low-pressure turbine. The steam that has completed its work in the low-pressure turbine is actually not wasted. This steam leaves the turbine and then enters the condensate at the bottom of the low-pressure turbine. The condensate contains circulating cooling water. Therefore, the steam condenses into water upon cooling, and the condensate water is collected by a collector at the bottom. As the condensate cools the steam, the water in the condensate pipes absorbs heat, causing the cooling water's temperature to become very high. To lower its temperature, the cooling water is sent to a cooling tower for cooling. Now, let's see how the cooling tower cools this water. First, the high-temperature cooling water enters the cooling tower along hot water pipes. Cooling towers are made of concrete and typically reach heights of up to 200 meters. The interior of a cooling tower is not complex. It primarily consists of a basin, air inlets, heat dissipation fill, spray pumps, and a water reservoir. Hot water enters through the inlet and first reaches the spray pumps. Afterward, the hot water flows to the heat dissipation fill. The heat dissipation fill extends the residence time of the cooling water, ensuring it has enough time for thorough